You'll recall in a previous video we took a look at this system here where we had a track with some friction. There's a mass hanging off of a massless pulley, and we had massless stretchless string that was running over the pulley attached to a mass that was being pulled down the track. And at that time I observed that this force due to tension here on the blue system was equal to this force of tension here on the red system. And I did that by observing that the length of the bond stretch between each molecule had to be the same. Now I'm in a position where I can go and do this with a little more care. And normally what I would do in a case like this is I would put slash marks through here like these were third law pairs. Now, it's not a third law pair. It passes the test for same kind. It passes the test for equal, even though I didn't draw it that well. But it doesn't pass the test for oppositely directed. So technically, these aren't a third law pair. But what we often do when we analyze systems like this is we pretend that they are anyway. And I want to get into why it is that we can do that. And the answer is it relies on the microscopics of what's happening as the string goes around the pulley. So I'm going to draw a super duper magnified pulley with the string going off like that and around. And what I'm going to do is I'm going to draw several molecules on the string as we're going around the pulley, like so. So now what will happen is the bond between this molecule and this molecule got lengthened. As a result, we are exerting a force due to we'll still call it a force due to tension. I mean, technically it's an electric force at this point due to stretch the bond, but let's just roll with it and call it force due to tension here. And the same thing is happening here, but it's going to be directed tangent to the pulley, like that. And what's keeping it from going off the surface is there is a normal force being exerted by the pulley. Now it turns out that these two forces wind up being equal due to the geometry of the problem by the second law. And then we can look at, say, this one here. This tension here and this tension here, they're equal by the third law. And then this molecule here will exert a force due to tension on this molecule this way, and there will be a normal force to help direct us around. So these two forces due to tension wind up being equal by the second law. And then we go here. This gets stretched out. These are now equal by the third law. This is a different third law pair. This is pulling here, and we have a bit of a normal force from the pulley like that. These two forces of tension are equal by the second law. So as we go around and around and around the pulley, what we get is a collection of second and third law pairs. So here, these two are equal by the second law, then these two are equal by the third law, second law, third law, second law, third law, and so forth, until finally we're going along the string, and we can just say, again, it's the same deal here. These are equal by the third law. Let me just use an X here. And but that'll be equal to this force due to tension here by the second law. And this is because we're saying it's massless. Since it's massless, the net force has to be equal to the mass times the acceleration, but if we're saying that it's massless, that makes that 0. And so these are equal by the second law. But then this will be equal to it by the third law. I'll use black X's there, I guess. And then this would be equal by the second law, and so forth. So as we go around, molecule by molecule, we have equality via the third law and the second law alternating. Now, where this breaks down is if we make the string massive. If we make the string massive, then these two forces here will no longer be equal necessarily by the second law. If it's moving at constant speed, they will. But in this case here, they would be accelerating. And so this force here would have to be a little bit bigger than that force there. But with a very lightweight string, that's a pretty much negligible thing. But it does mean that with a real-world string, this force due to tension here would actually be slightly less, and I mean slightly less, than this force due to tension here. But if these objects are kilograms and we're talking about using a piece of thread that might only be a gram or something like that, this turns out to be less than a part per thousand difference. And so in the idealization that the string is massless, we can go ahead and pretend that these two forces are numerically equal. This sort of a situation crops up often enough that a lot of textbooks use the absolutely annoying turn of phrase, pair of forces that act as if they are a third law pair. And this is because, properly speaking, they aren't a third law pair. Like I say, molecule by molecule is a collection of second and third law pairs all the way along the entire string. But if you can pretend that the string is massless, at least they're numerically equal to each other. And so that's where they get that phrase, is because there are a lot of third law pairs involved. I've not ever seen any other phrase used to describe this situation. So technically it's not really a third law pair, but if it's massless, and then we can go ahead and say that they are a pair of forces that act as if they are a third law pair, which just simply means that they're the same type of force and they're equal in magnitude, but not oppositely directed. Alrighty, so going forward, we'll be taking a look at dynamics in 2 dimensions. See you over there.